What specific problem does your model address in the context of multimodal learning, and how does it improve upon previous approaches like late fusion models?
Our model addresses the inefficiencies and limitations of late fusion architectures in multimodal learning by demonstrating that early fusion models, which process raw multimodal inputs from the outset, can achieve comparable performance while being more efficient and easier to scale. Specifically, we found that late fusion models require a higher parameters-to-data ratio and do not offer inherent advantages when trained from scratch, as evidenced by our scaling experiments. In contrast, early fusion models benefit from reduced memory consumption and faster training times, particularly under lower compute budgets. Additionally, we introduce the mixture of experts (MOS) approach, which allows for dynamic allocation of specialized parameters across modalities, leading to improved performance and faster convergence compared to both late fusion and dense models. This specialization within a unified architecture enhances the model's ability to handle heterogeneous, multimodal data effectively.
How does the proposed method or algorithm work? Please illustrate the methodology step by step, highlighting any unique processes or structures in your model design.
The proposed methodology focuses on training native multimodal models, NMMs, from scratch using early fusion architectures, which process raw multimodal inputs without relying on separate unimodal components. The first step involves integrating text and image data at the input stage, utilizing a single transformer model that processes tokenized text and continuous image patches. The model is trained on a mixture of multimodal datasets, employing techniques like fully sharded data parallel, FSDP, and gradient accumulation to enhance training efficiency. A unique aspect of the model design is the incorporation of mixture of experts, MOS, which allows for dynamic allocation of specialized parameters across modalities, improving performance and convergence speed. The scaling laws derived from the experiments indicate that the number of training tokens should be prioritized over the number of active parameters, which is a departure from traditional dense model scaling practices.
Can you provide a simple, concrete example that demonstrates the inner workings of your algorithm, detailing the steps taken during the processing of a multimodal input?
In our algorithm, we utilize an early fusion approach to process multimodal inputs, specifically combining text and image data. For instance, when given an image and a corresponding text caption, the image is first divided into patches, which are then linearly projected to match the text token dimensions. Both the tokenized text and the projected image patches are fed into a single transformer model, which processes them simultaneously without relying on separate encoders. During this process, the model employs causal attention for text tokens and bidirectional attention for image tokens, allowing it to effectively learn the relationships between the modalities. This integrated processing enables the model to generate coherent outputs, such as captions or answers to questions about the image, by leveraging the combined information from both modalities.
What are the practical advantages of using your early fusion architecture compared to late fusion and other existing methods? Include specific metrics or findings from your results.
The early fusion architecture demonstrates several practical advantages over late fusion models and other existing methods. Firstly, our findings indicate that early fusion models trained from scratch perform on par with late fusion models, with a slight advantage in efficiency, particularly under low compute budgets. Specifically, late fusion models require a higher parameters-to-data ratio, making them less efficient as they scale. Additionally, early fusion models exhibit significant improvements when trained with sparsity, outperforming dense counterparts at the same inference cost. Our scaling laws suggest that for optimal performance, the number of training tokens should be scaled at a higher rate than the number of active parameters, which is particularly beneficial for early fusion models. Overall, early fusion models are easier to scale, consume less memory, and train faster, making them a more efficient choice for multimodal tasks.
How did you validate the effectiveness of your approach? Discuss the datasets used, evaluation metrics, and the experimental design that led to your conclusions.
To validate the effectiveness of our approach, we conducted experiments using a mixture of public and private multimodal datasets, including DCLM, Obelix, DFN, COYO, and a private collection of high-quality image-text pairs, HQITP. We primarily relied on validation losses as our evaluation metric, which correlated well with performance on downstream tasks. Specifically, we performed a multimodal instruction tuning stage, SFT, on the LLAVA mixture, reporting accuracy and CIDR scores across various visual question answering, VQA, and captioning tasks. Our experimental design involved training models with varying configurations, including early and late fusion architectures, and comparing their performance under the same compute budget. The results indicated that early fusion outperformed late fusion, and sparse mixture of experts, MOSE models consistently outperformed dense models, reinforcing our conclusions about the advantages of early fusion and MOSE in handling multimodal data.
What limitations or potential drawbacks were encountered with your proposed method, especially regarding scalability or performance across diverse multimodal datasets?
The proposed method, while demonstrating advantages in early fusion architectures and the use of mixture of experts, MOSE, encounters limitations related to scalability and performance across diverse multimodal datasets. One significant drawback is that while early fusion models are more efficient and easier to scale, they may not fully leverage the inherent heterogeneity of multimodal data, which could benefit from some degree of parameter specialization. Additionally, the scaling laws indicate that while early fusion models perform comparably to late fusion models, they require a higher number of training tokens relative to parameters, which may complicate scaling efforts as the compute budget increases. Furthermore, the findings suggest that different training mixtures yield varying scaling coefficients, indicating that the model's performance may not generalize uniformly across all dataset configurations. Lastly, the reliance on a single configuration for MOSE may limit the exploration of more optimal routing strategies, potentially affecting performance in more complex multimodal scenarios.